Chapter 11, Section 3 in the 8th grade note-taking guide is entitled Solving Equations with Variables on Both Sides. One definition here, definition of a literal equation. That's an equation with two or more variables. Obviously, if we have variables on both sides, we have to have at least two variables, if not more. So that's, of course, why that definition fits in here. Remember, we're talking about solving equations, something we spent the better part of 2 years talking about. So we're going to be using all those rules of solving equations that we already know. The rules of solving equations tell us to keep variables on the left and to put numbers or constants on the right. And when I'm talking about left and right, everything is in relation to the equal sign. Whenever I want to move something to the opposite side of the equal sign, I do so by doing the opposite. And remember, I'm allowed to flip the sides at any one time should I need to do that. So with all that in mind, let's go ahead and look at 1a here. 4x plus 6 equals x. Okay, so the rules say keep the variables on the left. Well, as you can see, I do have the variable 4x on the left, and that's really the only thing that's good about this because 6 is a number and it's on the wrong side. X is a variable, it's on the wrong side. So what I would be prone to do here is to go ahead and flip this around and rewrite this as x equals 4x plus 6. As you can see, when I do that, then I have the variable x on the left side of the equal sign, variables on the left, and I have the number 6 on the right side of the equal sign, numbers on the right. So then the only thing that's not so good about this is the 4x, which I'm going to have to move. Now, when I want to move 4x to the opposite side of the equal sign, which I do, I'm going to subtract 4x from both sides. Remember, I'm doing the opposite, and as far as the opposite here, that's all about the 4x, not this plus sign in the middle. The plus on the middle is stuck on 6. Think about this here, and you've heard me say this before. 4x is a positive thing. The opposite of a positive is a negative. Negative looks like subtraction, so I'm subtracting 4x all the way across here. All right, so I do that. That makes these go away, and so I've got x minus 4x, which is negative 3x, and it equals this guy 6. All right, a multiplication equation to be solved by division. And as you can see, looking at their work that was pre-printed, it's not anything different. It's exactly what we were going to do here. I'm going to divide both sides by negative 3, because now I'm going to isolate that variable, get him all by himself on the left side. Remember, when I want to move something to the opposite side, like the negative 3, since it's a number, I'm doing the opposite. It says I'm multiplying by negative 3, so the opposite is dividing by negative 3, which is what I'm doing. And when I take 6 and divide it by negative 3, I end up with a result of negative 2, which is exactly what you can see. The suggested solution there is, even though they took a different path to get there. All right, let's go ahead and take a look at number 2 here. Kind of a long problem. They've got lots of stuff here, but all we're going to do is consolidate this and undo what we just did. It's not anything different. We've got 10z minus 15 minus 4z equals 8 minus 2z minus 15. Now, as you can see, what they've done here first is they've consolidated what they could. They combined the like terms, which is something you're familiar with because we just did that in Chapter 11, Section 1. On the left side, they've noticed they've got the 10z and the 4z, and they can put those guys together to make 6z. Now, if you're wondering why I didn't do the opposite there, the reason I didn't do the opposite there is because I didn't move anything to the opposite side. They were on the left side. They're both still on the left side. They've just been consolidated. So I came up with 6z by doing 10z minus 4z, exactly what it says. On the right side, they consolidated the integers by doing 8 minus 15, same approach. And that's where they came up with this minus 7. This minus 15 on the left and the negative 2z on the right, I didn't consolidate those with anything yet because I haven't yet, nothing for me to consolidate with. I need to shift those to the opposite side, which is where they're going to go next here. All right, so we're going to send this 2z, the variable things, off to the left. As far as moving that, I'm adding it to both sides. Look, it's got a negative here. The opposite of a negative is a positive, and positive looks like addition. So I'm adding 2z to both sides. The 15, being the integer, is going to have to go over to the right side and join 7. And I'm adding 15 to both sides, again, me doing the opposite. And when I do that, I end up with 8z equals 8. And then it's a matter of me simplifying that. Well, of course, this is a multiplication equation. And even if I do it backwards, I still am going to end up dividing by 8 here. 8 divided by 8 changes into 1. So z, the variable, equals 1. All right, let's go ahead and continue on here and take a look at number 3. It says Daisy's Flowers sells a rose bouquet for $39.95 plus $2.95 for every rose. A competing florist sells a similar bouquet for $26 plus $4.50 for every rose. Find the number of roses that would make both florist bouquets cost the same price. All right, so take a look at Daisy's cost here. You're going to spend $39.95 plus $2.95 for every rose, which is exactly what you can see they wrote here, $39.95 plus $2.95 for every rose. Now the question wants to know, when would that amount be equal to, which is why the next thing you say is an equal sign there, the competing florist that sells them for $26 plus $4.50 for every rose, which is exactly what this side says, $26 plus $4.50 times the cost of a rose, or $4.50 times the number of roses. So we're going to solve that equation, and since they're asking me when are these two things equal, that's of course again why it's an equal sign and how I'm going to end up solving the equation here. Now, as far as solving this goes, this is again a little bit backwards. I would not tend to solve this like this. Not that the order needs to be flipped, but they're sending numbers to the right side of the equal sign, which I'm not really, or the variables to the right side of the equal sign, which I'm not too fond of. As you know, I would be sending variables off to the left here because variables belong on the left side. Remember, the reason we do that is because of inequalities. We want to set up these so they look like our inequality statements, because in our inequality statements, when I put the variable on the left side, the shading, when I make that inequality, will match up with the same way the inequality sign points. So I would be prone to subtract 450R from both sides here. And when I do that, the 295R minus the 450R is going to change into negative 1.55R. And then as far as the numbers, they're going to go to the right. So I'm going to send $39.95 over to where 26 is right now. And again, I'm doing the opposite to move it to the opposite side of the equal sign. So I'm subtracting. So I've got minus $39.95 there. That's going to end up giving me negative $13.95. Now, even though these are negative numbers, that's not going to be an overall problem, because realize when I'm about to solve here, I'm going to do negative divided by a negative, which is going to turn into a positive. That makes sense. I have to be selling a positive number of roses. I can't be selling a negative number of roses. So if I would have done this and I've said, oh, the solution is -7, they match up at -7 roses, it doesn't make sense. But here, the negative divided by a negative is going to turn positive, and it's going to work great. We're going to divide both sides by the negative 1.55 here. And when I do that, I end up finding that R is 9. So when I buy 9 roses from either Daisy's or the competition, I end up paying the exact same price for those 2 bouquets.